Recording. Okay, today is Tuesday.
I'm writing down
what
you say.
Good luck.
Oh. Okay, welcome Internet Juniors and DT Shetty, who is skipping this class. We shall learn about graph theory. How? Right now. So we have, recall that we have the most famous graph in all of graph theory, which is the graph which began graph theory. Yeah, so I'll just talk about like once again. There's like land, there's more land, there's an island, there's like a peninsula-ish thing. What do you, whoa. Something very embarrassing happened off camera. Alright, so, then there were various bridges. Here's a bridge connecting this island to this bank of the river. Here's another bridge, another bridge, another bridge, another bridge, another bridge, and another bridge. Okay, well, question. Can we march a parade through Königsberg in which we cross each bridge exactly once? Answer, after some exhaustive searches, seems to be no. How can you prove that this is impossible? Euler said, I can do this. In fact, I will prove something stronger, which is that no graph, on no graph is it possible to make a so-called Euler trail if there are more than two vertices with odd degree. And so what we do now, or only one, which is actually just impossible at all. Okay, so we have a situation like this. What we can do is we can interpret the various places where the bridges lead you to as sort of single locations. And now we have something recognizable as kind of like a modern graph. And this vertex, what's everyone talking about? This vertex has degree 3, this has degree 3, this has degree 5, degree 3, yeah, that's all. So we have, have I done this correctly? Yeah. Yeah, so here we have actually 4 vertices of odd degree.
What are the 7 bridges? What are the 7 bridges?
They're not, this, and I had the bridges up and then I drew over them. This was a bridge, this was another bridge, 2 bridges connected. Then there was another bridge connecting the island to this bank of the river. Then there was a bridge here, and a bridge here. So okay, good. All right, so we have the following terminology now. We have an Euler trail. Is it correct that we basically didn't talk about this at all last class, right? Yeah. But I did sort of keep homework on it anyway. Yeah. Good. Okay, and so an Euler trail is, what's a trail first of all? ET for VP, trails associated with edges. So a trail is a walk in which no edges are repeated. An Euler trail is a trail not only in which no edges are repeated, but every edge is used. Cool, say cool. Okay? And an Euler circuit, well, a circuit is a type of trail. In particular, a circuit is a trail in which you end back at the same vertex that you started. Yeah? Okay, so an Euler circuit is one in which you start at a vertex, do a walk, end at that same vertex, use every, do not repeat edges, and also use every edge. Use every edge exactly. Use every edge exactly once. Yes, Samuda.
So wait, I don't know, in chapter, in the first section, we talked about something where you can like invert a vertex edge map into an edge vertex map?
Yes.
What do you call that thing?
A line graph.
Okay, so if you have a line graph, then you can do an Euler-Hamilton swap, is that true?
I believe that is true. Okay. So, maybe that might fit. Okay, good. Wait, so do I need to move your seat? Good. Okay. Yeah. So good. Right. So here is the key theorem regarding these things, which we've already more or less talked out, but we'll do it with. Oh my God. Okay. So there is an Euler trail the main theorem is there's an Euler trail if and only if there are no vertices of odd degree. Euler trail, Euler circuit.
Yeah.
Euler circuit, if and only if there are no vertices of odd degree. Okay, we shall do the proof. Are you ready?
Yeah.
Okay, and this proof is in the book, and it's also kind of common sense, but it's still worth talking about. So, first we'll do the forward direction. So, suppose there is indeed an Euler circuit, and suppose Euler circuit, and what we will try to show is that there are no vertices of odd degree. Okay. Well, the intuition here is that as you do a walk through a graph, when you pass through a vertex on your walk, you use up one edge going into the vertex and one edge going out. And so if you have a particular vertex which lies along a walk, then you will use up precisely two edges, and so you will reduce that vertex's degree by 2. Okay. So if that's the case, then if you have a well, maybe we should just do this more properly. So suppose we have an Euler circuit. Show that there are no vertices of odd degree. Well, I guess we just suppose that there is a vertex of odd degree, and we get a contradiction. So suppose that the degree of some vertex v1 is odd. So suppose we have a vertex of odd degree. I'll show that this is impossible. Well, basically there are two cases to consider. What are the cases?
It's like the starting point or not the starting point?
Basically that's it, right? Yeah, a circuit starts at a particular vertex and goes all around and ends at the same point. So there are really two cases to consider. Whether this vertex v1 is the starting and ending point of the walk or of the circuit or not. So if v1 is the start end vertex, or if v1 is not the start and vertex. Well, and the argument is basically the same for both of them, right? If v1 is not the starting or ending point of the circuit, then each time we pass through vertex v1, we reduce its degree by an even number. And so it's just impossible to have that vertex being of odd degree because we cannot use up we must use up all of the edges, but to use up, we have to use up the edges in pairs, and so this is just.
Is there a more formal way of this?
I think he says it a little bit more formally, but I think it's basically he says. Well, he says.
Like that argument makes sense.
It's not the only way to slightly make it the way to slightly make it more formal is just to say, okay, suppose you have a vertex of odd degree. It's not the starting and ending vertex. As you pass through, you reduce by 2. So finally, when you pass through it for the last time, or when you use up the last edge rather, because by assumption there's no Euler circuit, so by assumption every edge gets used. So as you use up the last edge, then you just get stuck in v1, and so you can't leave again, and so there is no Euler circuit contradiction.
Like there's some underlying induction on the number of edges in the circuit.
Yeah, that is true. Yeah. But I don't know if you even really need to do that because.
You don't even need to induct.
Sorry, what's parity?
Wait, hold on. Let's be respectful of each other, sort of. So yeah, I don't think it's really induction. I think it's a sort of a combinatorial argument. Just that you must, if every edge gets used, then there's only one way. I don't know. Can someone say this more formally?
Because like really, it's really like formally you just have a set of vertices and a set of like, edges which connect them. So like, I don't really know because we're just sort of like I think that what we're saying is logically valid, but we're still just sort of like, oh, if you think about it, it's true.
Okay, so your degree is a number. Every time you go through it, that number decreases by 2. Right? Because you're going in and you're going out. So odd number minus 2 some amount of times cannot equal 0.
Wait, no. Yeah. We're not using modular arithmetic.
I think the weird thing for me is that every time you go in and out. Let's see. I don't know if
Yeah, so it's possible that if you wanted to do this very formally, that you would do an inductive type argument. I mean, you sort of are.
If you want to be more formal, just write it in a list. So you have a list of vertices you visit. If you do that list version where you go vertice, edge, vertice, edge, vertice, edge, literally going. Okay, so then you go like edge, vertex, edge. So the first edge is going in, the second edge is going out. That's just by definition of what a path is.
Let's call this good. Wait, I think we can call this good. Good. Okay. If and then you only have to modify the argument very slightly if V is the start or end vertex. So now if V1 is the start or end vertex, well, you still have the same problem, right? Because now suppose that the degree of this is odd. Well then, as we leave V1 for the first time on our circuit, we have reduced its degree by 1. So now the degree of the remaining edges coming out of V1 is even. So yes. Okay, so now each time, if ever, again, we pass through V1 on our circuit, we again use we use up precisely 2 edges. And so on the assumption that this is odd, there are only a even number of edges that can be left coming out of V1. But we need to also end at V1. So we need to save 1 edge left for when we re-enter V1, and there's just not one there. Okay, I'm going to call that good for the moment. I think maybe some person could make it more formal. Maybe I should try. I haven't yet. Okay, the converse is more interesting, and it's more sort of typical of something that's kind of new in graph theory, I guess. It's proof by algorithm. So, okay, we do it. So suppose now that there are no vertices of odd degree. This, I mean, to me, this seems intuitively a harder direction. If there are no vertices of odd degree, show that there must be an Euler circuit. And it really needs to be a kind of a, well, it doesn't need to be, but it is a constructive argument. So given any arbitrary graph, if there are no vertices of odd degree, I need to be able to produce an Euler circuit. Okay, and so I will do it. And I'll sort of do it by example. So let's make some graph. So I don't know.
I'm working hard.
And I can pretty much do whatever you want. So it's more fun. The more edges there are, the harder it is. Or the weirder it is. Okay, I need to have none with odd degree, so I better make more. What can I do to fix this? And just like one of these, maybe. Alright, how's that looking?
That one has 5.
Which has 5?
The one you just.
Oh, damn. No.
Yes.
1, 2, 3, 4, 5. So I didn't want to do this one. I wanted to do.
Draw it to the one above it.
Yeah. That one, right? Yeah. Or I could have just. Well, these guys have 3 relationships. Yeah. Brother, sister.
No.
Alright, stop there. Alright, good. Okay, nothing, doesn't matter. I didn't say anything. You can't prove it. Alright, good. So, we begin. I will call this vertex 1, vertex 2, 3, 4, 5, and D6. And then I'll also label these edges. Take a minute. 1, 2, 3, 4, 5, 6, 7. Why?
And now George is
What are
on
you guys
camera.
talking about, huh?
The Allens?
Were you not here last class?
No.
Sad without you. All right, good. So we start. Where shall we begin? I say we begin at B1, just because why not? All right, and what I'm now I'm claiming that the algorithm goes like this. And you know, the whole idea of it being an algorithm is we shouldn't have to put in any like intelligence into it. We should just be able to blindly follow it. Yes.
Wait, so you're not really doing it by example, but you're pretty much saying that
You're just going to do an example to show what the algorithm is.
The only thing, the more general proof would only involve lots of subscripts on such and
Yeah.
such.
And
So the algorithm goes like this. Pick a vertex arbitrarily. Well, first of all, do we agree that this graph meets the conditions, that there are no vertices of odd degree? Say yes.
Yes.
Okay, good. All right, now arbitrarily select a vertex, and what we need to do is we need to go on a walk, and we need to produce an Euler circuit. So what do we need to do? Two things. What are the two things in order to produce an Euler circuit?
All right, you have to go everywhere and like use up all the edges.
Use up all the edges,
And you have to be able to come back without going through twice.
and we have to not repeat any edge, and we have to end up back at V1. Okay, good. All right, so we begin walking more or less at random. So you just pick an edge at random. And then basically there are two possible things that can happen. You can find yourself back at V1, or what else could happen?
You could not be at V1.
Actually, I claim you have to get back to V1 eventually. Yeah, why is that true? If you just start walking, if you start walking randomly and you just keep going and keep going and keep going, you either end up back at V1, or
haven't used it.
you get stuck somewhere. But you can't get stuck somewhere because as the degree of every vertex is even, you will use up one on the way in, and you will always have an odd number on the way out. So you'll always have a vertex on the way out. You always have an edge available to exit from each vertex. So it's impossible to get stuck at any other vertex.
Without repeating.
Yes. Sorry. Yes.
Wait, then why do you need an algorithm? Isn't that like the end of your argument?
Oh no, because for example, let's just start, right? Suppose I start at V1 and I follow E9, and then I follow E11, and then I follow E8. Wah wah wah. So I did E9, I did E11, I did E8, but now I just found myself by randomly picking back at V1 again.
What's the problem with that?
Well, there's no problem, but I haven't yet produced my Euler circuit because I have to use every edge once, and I have edges remaining. Does everyone see how that has to happen? Okay. So now we arbitrarily pick. Oh, so claim if you should go on a walk and find yourself back at V1, check to see if there are any edges remaining. If there are no edges remaining, then you are just done. Because you've used up every edge, exactly, you haven't crossed over any edges twice, and because you've taken them out of the graph as you've used them, and you're back at V1. So if there are edges remaining, then, the other thing that's true is that probably need this guy to be connected.
Yeah.
Is that just like part of the theorem?
Yeah.
Does it say that somewhere? Like right there?
If it was disconnected, it definitely could not happen.
Wait, what's it?
Yeah, if it's if it's disconnected, yeah.
It's a connected multi.
So it probably even says this. Yeah, let G be A. This entire thing is only true if G is connected. So if
two separate.
G is connected.
No, a graph shows more than one.
Okay, so since G is connected, there must be.
Vertices are connected by more than one.
Okay. Okay, so then there must be a vertex somewhere along this path which has edges remaining. Why must that be true? That's actually a little bit subtle. So my claim is, in justifying the algorithm, that there must be vertices on the trail that we've constructed so far, which have edges remaining coming out of them.
If not all the edges are used.
If not, if not all the edges have been used. Yes.
Well, yeah. So like
just like
either
pause.
if your current if your current circuit includes it doesn't include all the points. We know it's connected. So like at least one of the vertices in your current circuit has to be connected to a vertex you haven't used yet.
Okay.
So then there's an edge there. And then if you've used, then the other case is every vertex is in your circuit so far. And then in that case, every edge is connected to the, like this.
Yeah, that's good. Wait, that's good. He's going into more detail than Bass did, but I think that's actually like good. So he says, okay, let's see if I can repeat this argument. He's like, yo, do your trail, circuit rather, actually, and you're back here. We know that this graph is connected. So the claim at this point in the proof, the claim is that there's at least one vertex in the circuit that we've constructed so far. In this case, it would be V2 and V4, which has edges remaining. So let's assume that we haven't used them all, so the algorithm's not done yet, right? So there are some edges remaining somewhere. Well, so claim is that there's some vertex in the circuit so far which has edges remaining. Well, as there are some edges remaining somewhere, if the vertices which have edges remaining coming out of them are not in this circuit. Wait, hold on. Say it again.
It's like you could do a proof by contradiction with this. Like if you only have some of the vertices in your current circuit, and then you assume that none of them have any more left and no edges coming out of them, then those vertices will not be connected to the remaining vertices in the graph.
Yeah, that's better. Yeah. So suppose that none of the vertices in the circuit we've constructed so far, which would be V1, V2, V4, have any edges coming out of them. Yet there are still edges remaining elsewhere in the graph that haven't been used. Well, if there are no remaining edges coming out of V1, V2, and V4, then it means that, does it mean that? Then it means that these vertices are not connected to the other edges, to the other vertices. But maybe they were connected, but we used up
If
here.
you used it, then you would have visited that.
Okay. Whoa. Okay, so it's actually like a multi-step argument. Let's try to say it one more time. Alright, so suppose there's some vertex, essentially like here's the argument, right? Suppose there's some vertex which is outside of the circuit constructed so far, but which still has edges remaining in it.
No, you can't use an arbitrary.
Well, it has to have
I
edges
can't.
because we're
Yeah.
assuming it's connected, right?
You can't use an arbitrary.
I got all this, but I'm having trouble saying it sort of all at once. Wait, I should just let him talk. Yeah, say it all one more time from the beginning.
It's like we have that it's connected.
It's connected.
And
Check.
then we have that we're assuming for this case that we've only used some of the vertices
Yes.
in the graph.
Yes.
So then, if we suppose for contradiction that no more edges remain from those vertices, then we have that there's either like there's no edge like connecting any of the vertices to any of the ones we have not used yet. Well, that's essentially what we're saying. There's like, or we've used it already. But if we've used it already, then we must have visited those other vertices. So that's a contradiction there. And in another case, if there are no edges, then it's not connected. So that's a contradiction.
Yeah. Yes.
What if you visited all the vertices but not used all the edges?
Yeah. So then in that case, then every edge is between vertices that are already in here. So any remaining edges.
But then it's even easier for us, right? We've visited every vertex, but there's still edges remaining. Then the only claim I need to make right now to continue with the proof is that there are some edges remaining coming out of some of the vertices that we have already visited, which they just have to be. Because again, by his argument, if there aren't any edges coming out of these vertices, but there are still edges remaining, then those remaining edges must be connecting like other vertices. But if they're connecting other vertices and not any of our vertices, well, first of all, if there are vertices that aren't in our group of vertices, that means we haven't visited them yet, which means they have no edges with any of our, well, it means we haven't visited them. So if there are no vertices connecting vertices, if there are no edges connecting vertices that we haven't visited with the vertices we have visited, then it means our graph is disconnected, which is a contradiction. Okay, good. That was sort of saying the same thing 7 times. Maybe none of them perfect.
Usually the best way to do our the proof is like with invariance.
Good. We continue. I know what you're talking about. Yeah.
It's way cleaner as an argument.
I like this though. Okay, so we proceed. I arbitrarily, for the next step in my argument, pick a vertex which has still edges remaining. Which one do you want to pick? How about V4? So I designate V4 to do a, I designate V4 to be a spot where I take a detour. And the detour will be just like a new a new circuit starting there. Okay, so how do I do this? Well, maybe I do like, I don't know, E13 or E13, E6, and again back to back along E7. All right, and I find myself back at V4. So then the same argument now repeats, right? That again, if I start at V4 and I just go out, I eventually have to end up back at V4. And the only way to otherwise I use up every edge. If I do use up every edge, then I'm done. If I don't use up every edge, then I might end up. I have to end up back at V4 again because I can't get stuck anywhere else. Yo.
You could just consume all the edges that go into V1 to do that.
That's okay?
But then you have to go back to V1 eventually.
No, I don't need to go back to V1 because it's a detour.
Oh.
So that's the essence of it, right? In between E11 and E8, I now decide to do E13, E6, E7, like so. It's just recursion. This is exactly what it is. Yeah.
Yes.
And so now, so this was like kind of like my stage one, like provisional circuit. And now my new updated circuit is E9, E11. In between E11 and E8, I instead follow E13, E6, E7, E8. Get it? So get it.
Yeah,
So get it. Okay. Again, I have not used up all the things. So by the previous argument, there again has to be some vertex along the way that that has edges coming out of it. So which one do you want to pick? Do it in a way to like make it maximally like annoying. That's like cool stuff. V3. Okay. So instead, let's take a detour from here. Where should I go?
12.
E12, E10, E3, no, we'll do one more of this. E4, now you just want to get this whole thing over with. Okay, so I did a big loop, and I have now inserted in between the E13, E6 step, I insert a walk of E12, E10, E3, E4, E5, and then back again. Okay, so now my like updated thingy is E9, E11, E13, E12, E10, E3, E4, E5. Why did I make so many edges? E6, E7, E8. Okay, now there's still one left, which is like say here, and so yeah, we do this, and then we do detour, detour, like so. Okay, so now in between, what was that, E3 and E4, I stick in a, did I even do that right? I think it was 4, 3, well, whatever. 5, shouldn't it be, no, I guess I went that way, sorry. E3, in between E3 and E4, I stick a E2, E1, and there we go. Yo.
How can you be sure that this terminates?
Okay, so that's exactly the conversation that we have to have. That we have to show that the algorithm is correct, that and that it does what you say it's going to do, and that it doesn't get stuck, and that it doesn't go on forever. Okay, why does it terminate? Well, we have a finite number of edges, and we keep using them. So it can't infinitely go on forever, because eventually we're going to run out of edges. So that's good. You don't repeat any edges. I mean, you have sort of like a list of edges and you take them out as you use them. Can you cap that marker? All right. So that's one consideration, right? That the process is sort of finite and it's heading towards 0 edges. And then the other thing is that by all the previous logic that we had, we can't repeat edges, of course, because we take them out of consideration as we use them. We can't ever get stuck not getting back to our vertex because the vertices all, by assumption, have even degree, and so we never get stuck at a town and can't leave. And what else do we have to say? So that shows that we've used every one. It shows that we've not used them more than once, and yeah, we win. That's it. Yo.
Okay, so like, if you were to do this completely rigorously.
Completely rigorously says no Singer, who has probably proved way more algorithm correctness proof than I have. You should show, he says use invariance, which I think what he's talking about is show that, present your algorithm and show that at each stage of the algorithm some quantity is invariant, and that is something like the number of something remaining, and that's always like even or something,
Yeah,
right?
you just like make some statement and then prove that it's true at every, that like, if it's true at one step, then it must be true at the next step.
It's like NIM, right? Where you keep.
Yeah.
Something like that, yes. Yes, in this case, I guess the invariance is, I don't know, I guess it's just the parity of the remaining, it's just the sum, that the sum of the degrees at every stage is just always even.
Yeah.
Something like that, yeah. I don't know, I thought this was good. So, cool. Yeah, I think those proofs end up being not really like constructive per se then, right? They just show, what
You
else?
still have to prove the algorithm terms.
You still have to prove the algorithm. Okay, good. I am satisfied, maybe you are too. The sort of corollary is that, about trails, which is that there is an Euler trail, if and only if there are, Euler trail and no Euler circuit. Euler trail and no Euler circuit, if and only if there are exactly two vertices of odd degree. Okay, so let's do it. Again, we'll just kind of talk this out. The forward direction I think is pretty chill. If there's an Euler trail and no Euler circuit, then we must show that there are exactly two vertices of odd degree. Well, based on our argument from before, that every time we pass through a vertex, we use up precisely an even number of edges, then if we have a vertex of odd degree, it must be one of the starting vertices. And so if we have a vertex of odd degree, as we leave, we use up 1 degree, and then the last one we use up as we enter it for the last time, we also use up 1 degree. So I feel like that's it. Is there anything more to say? Hold on.
So it's not 0, it's not non-numbered, and it's 2.
Yeah, I guess to really show that there are 2, we should consider all the possibilities, right? So one possibility is that there are no vertices of odd degree. So suppose there are 0 vertices of odd degree. Well, that's impossible because we are assuming that there's no Euler circuit, and we've seen that if there are none, then there is no Euler circuit. Can I kill that one?
Yeah.
Okay. Could there be 1 vertex of odd degree? No, that's just like literally violates handshake, right? You can't have a single vertex. You can't have a single vertex of odd degree because then the sum of the degrees of all the vertices would be odd, which is impossible. So 1 vertex of odd degree, just like no. This is probably a better way of doing it. And then how about greater than 2 vertices of odd degree?